So we will continue our discussion on branch prediction. So last class we saw a 2-bit branch predictor, the way it works, and I also extended it into a 3-bit and n-bit, and we also stopped with one statement which was empirically proved statement saying that a 2-bit predictor works as good as a n-bit predictor. Okay. Now all the branch predictions that we have seen are basically local branch predictors. They are local in the sense the decision that we make, whether it's a 1-bit predictor or a 2-bit predictor, the decision that I make for a particular branch, whether it is taken or not taken, is based on the performance of that branch, right, in the previous instances of execution. I have not considered any other branch. So if I am looking at a branch which is at say 1005, now the decision I am going to take at some execution of this 1005 branch is based on its behavior in the previous instances. There is nothing, I am not considering something other than this. Now, so is there something else that I can do, and is there some sense in doing that? That is what we will see with what we call as the global branch predictor, right. So should we do something better than this? We just saw some static things like not taken, always not taken, always taken, then we saw a dynamic 1-bit prediction and a 2-bit prediction. But can I do something global? So is there some, is there some compelling reason, or is there some motivation for doing it? Can you come out with some justification of why should I look into something called global branch prediction? What is global branch prediction? The decision that I need to take of a particular branch depends upon other branches that are recently executed. Can you get some examples in favor of this? So can you get me a simple C code?
Yes.
What is else?
Nested for loops.
Nested for loops, no. Nested for loops would have worked even with your just not taken or taken. If else statement what? If else will be only one jump, no. The question here is that the decision for 1005 is based on some branches that are close to it. Can you give me a motivational example for this? Very simple example. So I am looking at global branch prediction. That means I am looking at more than one branch. The decision I want to take for a particular branch, say B, depends upon some other branch that has been that has some other branch situated at some other address, right. I identify a branch based on an address, correct. So then what will I decide? For example, I have switch, long since I used this I, correct, and I have case A, case B, which are all conditions, case C, default, and in each I will have a body followed by break. This is a switch case. So now can you tell me anything about this? Can you give me a very simple example? Obviousness is the enemy of correctness. Can you give me an obvious example? Say suppose I have a branch for A, suppose I have a branch for B, C, etc. Suppose A is not taken, do you mean to say B will be surely taken? That anyway we have, yeah, that's why we have prediction. What are we gaining there? See, that's not a, chance is not a motivation, chance has been the motivation already. So chance cannot be further motivation for this. Surely that should happen. See, that motivation is something like there is a case where it is going to absolutely happen. Chance is everywhere there. So let me write this. if I equal to 2, let me say A equal to 0. If J equal to 2, then B equal to 0. Let me say this is branch 1, this is branch 2. So, if B1 and B2, meaning this condition, let me call it, are true, then B3 is false, correct? Correct? So, this is a very common code, you can see, very simple code, correct? So, now whether B3 will be taken or not can be inferred from whether B1 was taken, or suppose let us say if the condition is true I will take it, okay. Let us assume if the condition is true. So, if this condition is true and this condition is true, surely I will know that this is not going to, this is going to be false. So, I can infer something about this third branch depending upon the behavior of branch 1 and branch 2, correct? Fair enough? Okay. So, this is what we mean by a global branch prediction. Okay. So, there is a motivation for this, and this motivation will not come from your for, while and other structures, it actually comes from internal statements. So, if I have a 10 million times executing loop in which I have these 3 constructs, then it is worthwhile for me to now take this type of a correlation there. It is actually the logic that is inside the body of a loop which results in lot of conditional jump statements which can basically get some favor from this type of a global branch prediction. Okay. So, this is what this is one motivation, this you will see in all the books, this is one, slight variations of this can be there. So, this is one motivation for why I should look at branch prediction, global branch prediction, and this global branch prediction is a part of some if else structures inside a loop. It is, this global branch prediction may not be that useful or that hilarious if I am going to look at while loop, for loop or do while loops. Fair enough? Okay. Now, how do we infer a global branch predictor? How will I infer that this branch is going to be basically decided upon by previous branches? Can I look at a 1 million line code in which there are several if else statements, and there can I go and make this type of inferences? This is one story. The second story is how do we actually implement this in practice? These are all concepts of advanced computer architecture, right. So, you take the elective computer architecture, MTech elective if you want in your subsequent semesters, and there we can see how these things are constructed. So, what I am also trying to tell you, all of you, that what you can expect in a computer architecture course. Now, you have done computer organization architecture, BTech mein sab kuch kiya hai, should I do something more on architecture? Yes, lot of things are there. So, you have an advanced course which will teach you much more, okay. So, keep that in mind. So, how do we construct the real architecture, how do I construct a real architecture which will handle global branch prediction? How do I even infer? Like somewhere I should do some pattern analysis and infer. So, these are all stories that I will leave for you. But even now we see there are very modern computer architectures still using static prediction, okay. So, the story that I have been telling and the story which I can take forward and talk more, right, on global branch prediction and etc., these are going to be something which are not so practical in life, okay. They are very good to be on paper, but zero on wafer, okay. It can be a very good ISCA, BUSCA paper, but then if you actually try and implement it on the wafer, it goes for a toss. It will need another nuclear power substation to basically power this. So much things that just for a branch does not matter. Now, the next question comes, how do we implement this prediction? So, next, what should be the next immediate question that you need to answer? We have been answering this query. So when we did this memory aliasing for load store, right? What was it that, how did we conclude? How did we conclude? What was my last statement regarding memory aliasing? That it could be efficiently implemented, and that we used a content addressable memory which had only the number of locations in that content addressable memory was equal to the number of load store units, correct? And that is why we said that this can be implemented trivially, because we will have only 4 or 8 load store unit and having an 8 address gap. 8 address content addressable, 8 location based content addressable memory is very easy for us to implement. Now the story is, now I am having branches. How many branches will I have? I will have a lot of branches. Not be 1, 2, 3 and all. It will be many. Now how do we implement this? How do I implement the branch target buffer? What is done is told. Now how do you implement it and why do you implement this? What, how, why, right? So how do we implement this branch target buffer? What is this branch target buffer? The way I described this was, it is a content addressable memory. So what do? I just give the address and then find out whether it is a branch or not, and then I start making a prediction. Okay. But in practice, how do I do this? Because I will have lots of branches, and if I am going to make a content addressable memory, say with 32, even 32 branches, I am gone. That will be a very huge hardware. So the way this is implemented is that you take the program counter actually has a 32-bit address, okay, if it is a 32-bit address. I will just take the first, it's say 6 or 8 bits, and I will take this 8 bits into index into this memory. So this is basically a RAM. Your CAM is implemented as a RAM in which the first 8 bits are used for, so this RAM will basically have 8 bits means 256, right. So 0 to 255, and I will use the first 8 bits to index into this, right. And here I will hold a tag of the remaining 24 bits, right, and then I will have the prediction bit. So I will have that tag here, I will have the prediction bit. So okay, you are able to get what I am trying to say. So now what will happen is, every time the 8 bits, the last 8 bits of the PC is indexed into it, and you get the data, you get the tag bit. The tag is, you get the tag plus prediction, and if this tag matches this tag, the remaining 24 bits, then we know that this is a. Otherwise what we will do, we need to we'll think it is not a it's not a branch, and then we will proceed, right. So every time my 8 bits will be taken, for example in this case, and we will index using that 8 bits into this memory, and then get the remaining 24 bits and compare it with the actual 24 bits of the PC, and then if it matches, then it is a conditional jump, otherwise it is not a conditional jump. This is how the CAM is implemented. So this is not strictly a CAM, but this is the easiest way for me to implement, because if I go beyond 32 entries, the CAM becomes very costly to implement. Okay. Now, so what are the problems in this implementation?
If two things have the same last 8 bits.
Yes, if two things have the same 8 bits, then I will collide, right. Then I have to completely replace this, the previous entry, and put here. So if I put, if I want to kill this technique, I put 2 branch statements exactly 256 apart. So this will replace that, that will replace that. So every time this jump will come, it will not find itself, it will find the other jump, and vice versa. Correct? Able to get this? So I can go, and if I have a direct map like this, I can have a scheme which will basically kill the performance. On the other hand, a compiler which is trying to fine tune this will see that the jumps are not 256 bits aligned. It will also try to check out that these fellows are not 256. So this is another intelligent thing which the compiler can do, so that I could get better branch performance. Are you able to follow? So the moment I make some restricted assumptions like this, I start hitting certain very interesting cases like this, right? So the compiler can see what is compiler optimization for an architecture. This is a very, very interesting, important question. We have talked of a couple of optimizations already, correct? Right? What was the optimization that we talked in the previous class? If I have always not taken as a static branch prediction, then a do while statement can be converted to a for or while statement, right? I can. So this was one interesting optimization that we saw in the previous class. Now this is another optimization. I will not put two branches exactly 256 apart if I am having such type of a predictor. The next thing, what should be the next refinement here? What could happen if this process goes and another process comes and sits in the same location, right? One process is completed, the things are freed, another process comes and sits in the same location, and then I start executing it, and then if this branch target buffer is not cleaned, then you go and say that this is a jump instruction. Actually it may not even be a jump instruction. If an entirely new program comes and sits in the same place of the old program, then what we need to do, your entire branch target buffer should be flushed. That means all entries have to be invalidated. So what do you mean by invalidating the entry? Should I go and make all this as zeros? Can I go and make all the entries here as zeros?
What is the need to flush it? Or what is the need to flush it?
Because otherwise what will happen, some other instruction, it may be an add instruction that will be loaded in the same as the previous jump.
But when we do loading, it automatically takes care of flushing.
What takes care of what?
We load an instruction.
When I load an instruction, who is going to take care of adjusting the cam, right? See, previously in 1005 there was a jump instruction that got loaded as 1005 here with some prediction bit. Now I remove that code and I am putting some other code there. Operating system, that program completed, it is gone. Now I am putting some other code there, or I did some garbage collection and I moved that code above. There are different reasons for why a code should not stay in the same place. It can move, it can migrate, it can be pushed. When I do that type of a thing, what will happen? If I am not going to flush this BTB, then when some 1005 it can be some add instruction that will be recognized as a jump, and for some stupid reason after add some other thing would be fetched rather than this. You are getting this? If I don't flush it, then after the add some arbitrary instruction will be fetched. Not only it will be fetched, if that particular instruction is outside your segment, it will give you a segmentation violation. Please understand, correct? The target need not be within the segment, right? It's a new program. So suddenly 1005 go and fetch something in 5000. In the new program it's an add. So when after add you suddenly see it is going to some 5000 and it is creating a segment jump. So you are killed. You understand what I am trying to say? So when a particular program finishes, then all of this has to be wiped off. What do you mean by wiped off? It has to be invalidated. How do you invalidate it? Can I go and write all zeros in all the locations? Then it is going to be extremely costly. So in all these type of entities where there is a need for me to invalidate it at some point of time, I will have something called a valid bit. If that valid bit is 0, that means this entry is irrelevant. If the valid bit is 1, then only this entry means. See, so the moment I switch on any hardware, all these entries will be some random zeros and ones, correct. So each one of them will represent some tag or other. But then what will happen, so what we will try and do is that we will go and make this valid bit 0, then we say that all the entries are invalid, right. So for me to flush the BTB, flush the branch target buffer or invalidate the branch every entry, I need to go and set only the valid bits of all these things to 0, then automatically everything will be in place. Rather than going and making all the entries as 0, I go and make the valid bit alone as 0, so that when the process tries to access it next time or the process tries to access it next time, it will end up with a error, okay. So we will also have this valid bit, and that is very, very important. So one thing is to flush the branch target buffer to invalidate all the entries in the BTB, we can use this. And very interestingly, when the system boots up, right, what is the reset value for all? What is the reset value for all? Already when the system boots up, there is lot of activity that is happening in there. That's why when I switch on the system, the initial power is a surge. Initial power consumption is a surge. It actually consumes lot of power, right. So that makes the entire problem very, very complex, okay. So if I am going to say on reset all these tag bits, prediction bit, everything has to become 0, then it will take enormous amount of power for getting this done. So what normally we need to do is, when I switch on the power, I do not want to invalidate the entire table, I will just go and make the valid bit for the entire table as 0. That is enough for me, as you see here. So I need not go and make all the tag bits, R bits, predict bits, everything 0. Rather than doing it, I can go and say, right, go and make this valid bit 0. That becomes very easy. And the reset pulse also should be a thug wire, because it is going to reset say some 500,000 transistors at one shot. So normally, right, the reset is a reset will be a tree, reset tree. So quickly we will reach each of these nodes and reset it. So the reset in this case, what do you mean by reset in this case? The reset in this case has to go and make this valid bit alone 0. So the amount of thugness the reset needs, that is reduced here considerably, because the reset is not responsible for going and erasing everything inside that RAM, but the reset will just go and make the valid bit. Once I know that the valid bit is 0, the entire other entries in the RAM in the branch target buffer becomes useless. The next thing that we want to see is called a tournament predictor. So this tournament predictor is an example of some sort of a machine learning that we do. So what happens for a particular branch, I will start with static prediction. Sometime when I see this is growing, we can make it as a dynamic prediction. So I can use 1 bit, 2 bit predictors, right. So here itself I can make a 1 bit, then I can if that is not suiting me, I can make it 2 bit. I can go ahead and make it global. I can return back the same way, okay. So essentially I am trying to play a tournament here, and depending upon my status, depending upon the the type of game a branch is playing, the predictor also is adjusted to meet that game. So if it is a for do type of things, then it will meet it to always not taken type of thing. But if it is something beyond for do while, where I gave some examples, then some sort of global prediction can also happen. So the hardware decides for every address which stores a branch, it will decide for every such branch based on that addresses. It will find out which mechanism of the available things will suit that particular branch. And so when I go in for that particular branch, when I am trying to predict, I will use that mechanism, like if a particular branch has to be evaluated globally, then I go to the global predictor, otherwise I can do it on the normal. Right. So this is the basis of what we call as tournament prediction. Okay. Okay. So the last bit is, of course, what we yesterday called the zero cycle instruction, which is nothing but the unconditional jump. Suppose I have like a branch target buffer, I also have an unconditional branch target buffer. In that unconditional branch target buffer, I actually store the branch details and the target address. I store the branch details and the target address. Branch details in the sense my program counter value and the target address. Immediately I will have the target address. So let us say at say some 1015, I have a jump on non-zero statement, jump on non-zero some L1. Okay. Now what I will store here, so I will store here 1015, I will say if it is non-zero and then the target address is L1. Now what happens whenever this instruction is executed the second time, 1015 is given to the branch target buffer, and that fellow will tell you whether it should be taken or not taken, etc. So this particular table is for conditional jumps. Now I could have another table for unconditional jump which says, say in 1020 I have just jump, just jump. This is an unconditional jump. So I can now say that 1020 and this is the target address, say L1. So how do I execute the instruction? I fetch an instruction plus increment PC, correct? This PC will now point to the next instruction. Okay. Now what will happen is, when I fetch an instruction, say let me say I have fetched the instruction at 1019, then I increment PC, it becomes 1020. The moment I increment PC, I will go and give it to this table. This table will, I will go and give it, I will just go and check this table. The moment I increment PC, currently I am going to execute 1019, so I have fetched instruction from 1019 and I increment PC. The moment I increment PC, it will go here, and here it will find 1020, right. So 1020 is it will also find L1, what is the target address. Okay. So at the end of the moment I increment PC and I find this, instead of loading L1, instead of loading anything, I will go and load PC with L1. So the next instruction that will come, right, will be L1, will be the one in L1. So when I am trying to execute 1019, after I finish 1019 I increment my PC. Once I increment the PC, in that cycle itself I will go and check whether the PC is stored there. It is not stored here. So 1019 I am executing, after 1019 I increment PC 1020, I go and check here, yeah, 1020 is loaded. I am not even fetched 1020. What I will fetch is the instruction at L1. I will not even fetch 1020. I am executing 1019, I have fetched 1019. Now I increment the PC, that became 1020. I now go and ask that fellow, is 1020 stored? He says yes, then I know for sure it's an unconditional jump. I will say then give the target address, he returns back L1. So the next that I am going to load will be the instruction at L1. So this 1020 wala never even executed or never even fetched into the system, and that is why we call this unconditional jump as a 0 cycle instruction, because it has executed. The unconditional jump has actually taken place, but what has happened? It never executed, correct? Because L1 was not even fetched. Without even fetching L1, the without even fetching this jump L1, which is there in 1020, I have finished the execution of it, correct? Let me just very quickly explain. 1019 I am executing. At that time I increment the PC, it became 1020. The moment I increment, I give to this fellow, and if he has an entry corresponding to that address, he will tell me what is the target address. That target address L1 I load. So the next, so PC was holding 1019, the next thing it will hold is going to be, the L1 address. So PC will never point to 1020 at all, right? So that means this instruction, this jump instruction never came in and got executed at all. It was just at the periphery level. So this type of jump execution of, not every jump can be done in 0 cycle. The execution of this particular instances where the unconditional jump can be done in 0 cycle, because jump I did not even fetch that jump into my system, but the effect of its execution is already got it. Are you able to follow? So this is a notion of what we call as a 0 cycle instruction. Thanks.